We have learned how Faraday discovered the link between a change in magnetic flux and induced EMF. Now let's investigate how we can make the flux change and induce an EMF in a conductor. One way is to change the magnetic field, and the other is to have a stationary magnetic field and move the conductor. But what do these actions accomplish? So how can we change the flux linked with a conductor? There are two ways of doing this. One is to change the amount of magnetic flux, and the other is to change the position of the conductor in relation to the source of flux. And that brings us to a working definition of motional EMF. From the above discussion, we can reduce the definition for motional EMF, that is, the induced EMF due to the motion of an electric conductor in the presence of a magnetic field. Let us derive an equation for motional EMF. Consider the given picture, which shows a rectangular conductor PQRS. Let's say a part of this conductor is movable, that is PQ, and this conductor is moving in a constant magnetic field. Conductor PQ is free to move and is also in contact with the conductor RS. Now, rod PQ is moving to the left with a velocity v, and PQRS forms a closed conductive circuit, and the area inside the circuit changes as PQ is moving. Since PQRS is placed in a uniform magnetic field B, and RQ is equal to X and RS is equal to L, we can say that the total magnetic flux, that is phi, is equal to B times L times X, where X is changing with time, and so the rate of flux is also changing with time, and that is inducing an EMF. As we have already learned, the EMF is equal to the negative rate of change of flux in the given system. So E is equal to negative d phi by dt. Since phi is equal to B times L times X, we can say that the EMF is equal to the negative time rate of change of BLX, or negative d by dt BLX. Since B is constant, that is, the magnetic field is constant, and L is also constant, we have a new relationship, negative B times I times dx by dt. Now, dx by dt is the rate of change of displacement in a sense, so that is equal to a velocity. It is negative here because the area covered by the rectangle is decreasing with time. So we have a new expression for the EMF, that is negative B times L times negative V equal to positive B times L times V. So here we see that in this loop, the rod PQ consists of charge carriers and a Lorentz force is acting on it, which is equal to QVB, since the rod is composed of conducting materials. Q is the charge in the section PQ, while V is the speed of the rod and B is the magnetic field. So based on the Lorentz force equation, we have W is equal to Q times V times B times L, where E is equal to W times Q, that is the EMF. So let's summarize what we have done so far.
Manorama Horizon. Learning made simple.